We studied node level measures. Now we are looking at edge level, essentially, measures. So in previous examples, in basically the first section of the class, we were looking into characterizing each node, and we were using centrality to basically do that characterization. Now, and we were using that, for example, for any, type of node classification. That feature that we found can be the input for a machine learning pipeline to distinguish between different nodes, for example. But in some problems, we want to study a pair of nodes. So we want to see how two nodes are similar to each other. For example, when you surf web, there's an option that, find similar pages. That will essentially give you nodes that are similar to this node on the web graph. And sometimes you just want to find if two nodes are connected to each other. So if two nodes are connected to each other, they are basically, you want to predict basically a higher similarity between those two nodes. So for example, let's say that I'm friend basically with you guys also have another friend. Sooner or later, you will introduce that guy to me. So it shows that I have too many, so I'm basically higher similarity with that node. So a prediction model will say that, so for example, on Instagram, you have many mutual friends with someone, sooner or later, it will suggest you that, hey, do you know this guy, add him. So that's the idea. This type of methods are the idea. And we should do that usually with using a similarity matrix. The similarity matrix is a square matrix. Let's say that we have n nodes in our graph. It is gonna be an n by n matrix, where each element in that graph shows the similarity between the corresponding nodes. So let's say that I have a matrix S, Sij is representing the similarity between nodes Vi and Vj. So that's the general idea with edge level tests. We want to define a method to find this matrix, this similarity matrix. There are in general three methods to find the similarity matrix. One is path-based methods. The other one is local overlap measure. And the last one is global overlap measures. All right, so in path-based measures, we look at the shortest path between two different nodes. So let's say that I'm looking at how similar V1 and V2 are. And I'm also at the same time looking at how similar V3 and V2 are. So the shortest path from V1 to V2 has length 2. There are two edges between the short path from V1 and V2. At the same time, there is a path of length 2 between V2 and V3 as well. So that will indicate that V1 and V2 have the same similarity as V2 and V3. But if you look at this graph, we will see that there are three shortest paths of length 2 between V1 and V2. And there is only one shortest path of length 2 between V3 and V2. So that will essentially tell us, logically, we will think that, okay, since there are too many paths from V1 to V2, and only one from V3 to V2, so the similarity of V1 and V2 should be more than V3 and V2. So the problem with this path-based method is that it does not take into account the number of paths between those two nodes. So for that reason, people use local overlap methods, which looks at the neighborhood of the nodes, and it looks how much of the neighborhoods of those two nodes overlap. Essentially, how many neighbors do they share with each other? So let's define this as Sij. So basically the similarity between nodes Vi and Vj is represented by the number of common neighborhoods between Vi and Vj. And someone can use this type of similarity matrix to do, for example, link prediction. You can define a threshold and say that if the similarity is higher than some value, I predict that there is an edge between those two nodes. Now, there is the issue with this type of essentially definition is that you don't really know, for example, let's say that two nodes have 3 neighbors in common. You don't really know without seeing the graph. Is 3 a lot? Is 3 not a lot? Does 3 mean that they're too similar to each other? Or they only have, a few, they have a ton of, connections, but only 3 of them are mutual connections. So it doesn't say anything by itself. So naturally, we will think that, we need to normalize this using some measure. And that normalizing measure, there are multiple of them. And the first one that comes to mind is that we divide this number of common neighbors by the total number of the nodes in the graph. So these are 3 neighbors, and we divide them, for example, 5 other nodes we have. We divide that, for example, by 10. But then think about the case that there are 1 million other nodes in this graph. So that's going to be 3 over 1 million. In the previous case, it was 3 over 5. But if you look at these 2 nodes, in any case, they only have these 3 nodes as their neighbors, and all of them are shared. So they should be highly similar, no matter how many other nodes we have in the graph. So because of that, it doesn't really make sense to use the total number of the nodes in the graph as a measure for normalization. There are 2 other nodes. There are 2 other methods. One is called Sorenson similarity. The other one is Jaccard similarity. In Sorenson similarity, we basically normalize this by the average degree of those 2 nodes. So in this scenario, each of these nodes had 3 neighbors. So both cases is going to give us 3. And we divide that over 2. So the output is going to be 1 because 3 shared neighbors, 3 degree each over 2 is going to be 1. Another method is Jaccard similarity. It normalizes the number of common neighbors with the total number of unique neighbors that these 2 nodes have altogether. So again, if we go back, each of them only have these as neighbors. So the number of unique neighbors in total is 3. The number of shared neighbors in total is 3. So when we normalize that, the output is going to be 1 again. So both of these 2 methods take into account that, they only take into account the local neighborhood of that node.